instead of maximal running speeds.
Alright, my topic is body size, gait mechanics, and maximal running speeds. So we're going to start with something different. So we're going to start with a race. So in a race, LeBron James and Simone Biles. So I'm going to ask you a question. How many of you think Simone Biles is going to win that race? So what's the race? We're going to just run them down the corridor. Okay, so just raise your hand if you think Simone Biles is going to win that race. Okay, now raise your hands if you think LeBron James is going to win that race. Okay, so I guess that right. So why do you all guess that a tall person is going to win the race? Okay. Okay. So at the performance lab, we don't guess, we test. So we tested that. So we tested data, a bunch of world's fastest runners, and we found out if tall person are really fast. Well, we found out that sprinting is really specific, right? It's a specific task to what people are doing there. They've been training for decades and decades. So there should be a single body type phenotype, right? If it's a specific task based on your answers, a tall person should be fast. So all sprinters, fastest sprinters should be tall, right? That's not what we found. So we have sprinters all the way from 5 feet 5 inches to 6 feet 5 inches. So there's a big size difference even in their height and even in their body size. So there are sprinters all the way up to 66 kilograms to 96 kilograms. Why the size difference? Based on the answers, tall person should be faster. Why is there a size difference between sprinters? Well, let's come back to the race now. We have LeBron James, Simone Biles. We know their height's different. Now, what if we have a way where we can scale them to a similar size? Wouldn't that make the race interesting, right? Right? So we have a guest today who has a really advanced technology that we can use. He is the inventor of the shrink ray. So he's going to help us enlarge Simone Biles to LeBron James's height. So now the heights are similar. So now who's going to win now? Which makes it interesting, right? So based on this technology we have a similar, which leads to my research question, which is do the maximal speeds of the swiftest human runners vary as a function of height? To test this question, we use Froude number. What is Froude number? So a generalized explanation for Froude number. Froude number tells you how fast somebody is for their size. So that's Froude. He used Froude number to identify the speeds of ships based on their size. Then Adam Cantor came in and he used Froude number to identify the speeds of dinosaurs. So I'm going to use Froude number to identify who's going to win the race. So we have V, which is top speed in the top. Then we have G, which is gravitational acceleration, which is constant. And then we have L, which is leg length. So going to the methods, like I said, Froude numbers, what Froude number tells us is how fast somebody is for their size. So we use 37 male national and international sprinters who ran on treadmill, a special treadmill, and also over ground under motion sensor technology. They ran less than 2 seconds at their maximum instantaneous velocities, and the speed was 10.5 meters per second to 12.09 meters per second. That's between 23 miles per hour to 27 miles per hour. So all of them were elite sprinters. From there, we found their height, we got their body mass, we got their leg length, maximal sprint velocity, and from that, we calculated their Froude numbers. So going to results, this is my mean plus the minus standard deviation for the data set. As you can see in the ranges, they vary a lot. The height is between 1.65 to 1.96, which is good for my study. So it shows this variation, and you can figure out the Froude numbers for them. If you see in the velocity, it's between 10.5 to 12.09, which is again a great variation. So what did we find? So on the y-axis, you have Froude number. On the x-axis, you have height. So what did we find? There was no relationship between Froude number and height. What does that tell us? That just means taller sprinters are running fast, not because of their height. Okay, so that tells us, gives us to the next graph, which is on the y-axis, you have max velocity, and on the x-axis, you have height, so you see a slight increase in taller sprinters. Let me get back. Taller sprinters are running faster because of their height, so you can see a slight increase in their speed there. So in absolute terms, taller sprinters act faster at top speed. In the discussion, since we found out the Froude numbers were similar, that means taller sprinters were faster in absolute terms. And since the Froude numbers are similar, that also means tall and short sprinters are running similarly dynamically. So they run the same. So tall people are just the scaled up versions of short people. So which brings us back to the question, why the size difference in these sprinters? If tall sprinters are good at top speed, why there's a size difference? Well, there's more to sprinting or running than just top speed. There's more things going on. Well, based on data, we can say that the tall sprinters are good at maximal running velocities, but the study by McKillen and Wayne told us height may impair acceleration, which is a big part of sprinting. So that could give us the answer, which is my next study, is find out the acceleration mechanics. But which brings us back to the question, who would win? So now you know tall sprinters are faster at top speed, but the acceleration, that's where you're going to lose. So again, I'm going to ask the question, how many of you think Simone Biles is going to win? How do you know she's going to get an acceleration of performance enhancement? Okay, not a lot of people. Now, how many people think LeBron James is going to win? Okay, well, the real answer is Michael Jordan. Questions? Based on the studies that we have, but the goal was to hide, since Froude number tells us how fast somebody is or the height, so it's giving you relative speed based on their linear. So that's how you can tell like if they're running faster, their gait is different based on the Froude number. So that's where we use height and Froude numbers in that graph to show, and we did not find any relationship between Froude numbers and height. We could have found a relationship, we could have show different results for that. Does that make sense?
Right. Well, because like the leg, I think the leg length, like I'm a leggy person. And
yeah.
So we can be like the same height as me and we have leg length, so we would be the same height without different numbers.
Yes, so height does give you advantage at top speed since because you have longer legs. But why don't we see the difference that in sprinting? It's just because you won't be as good as a short person in acceleration. That's why we see the bigger size difference in there. But that was the whole question. And like I said, if LeBron James is gonna beat Simone Biles, most people think it's just because he's tall. That's what he does that. That's what the question was. Who is I'm taller than gonna be faster than somebody else?
So the whole study is based on the concept of Froude number. Let me ask you this more fundamental question. How trustworthy this Froude number is?
Well, they have used it for finding out speed of dinosaurs. doesn't change as much as velocity changes more variably than the wavelength that we have. So, overall, to answer your question, I just got backtracked that it is used for gate transitions, you're correct, but based on the data that we found, it doesn't seem to correlate well.
This is the problem I face. When you run correlation, for example, with large data range, you can easily establish a correlation between the two variables, let's say.
Right.
But when you focus on the homogeneous group, then certainly the correlation goes away. It's not just because of the data range, but the nature of the relationship you're looking for. If you have a lot of group differences, then it already drives a strong correlation when you put all these together.
Right.
So sometimes some of the measures that develop for comparing different species over very different body sizes and so on, that may be quite useful. But when you try to apply that in homogeneous group with these cellular differences, for example, body composition and so on, then that may not be that useful. So I don't know much enough.
Are you suggesting control body composition and then you do
No. So my question is it really a good approach to use the Froude number to look at the difference among the specters? Is it that sensitive? That's the point.
How is that sensitive to the whole?
To really see the differences among
in
them.
this case? Well,
I mean, if you pay attention to the physical medium of this, velocity squared divided by gravitational acceleration times the length. It may have been used in many studies, but to me, who has a background in astronomy physics, doesn't really mean a lot. Just look at the variables used in, the parameters used in the equation. So the question is it really sensitive to differentiate one athlete from another?
for me, I think, since Froude number is really respectable to see gait changes, like how students go from walking to running, whereas like everybody has to be at the same Froude numbers, I think that's really respected in literature. That's what we use to find out. So basically, we use Froude numbers to figure out if they're running the same gaits overall.
Yeah.
I understand your question.
All right, so the next session starts at 11:45.